Today's lesson is 3.7, Linear Inequalities in Two Variables. Our two main objectives here today are to discuss the similarities between graphing lines and graphing inequalities on a coordinate plane, and then second, to learn methods of shading the solution set of an inequality or systems of inequalities. Now, what you want to remember is that this is very similar to solving one variable inequalities, where we had to use our number line and shade and look for an overlap of two sets to find the region in which the solution lied. So it's going to be the same thing in these graphs, but we're going to look for shading on a two-dimensional plane instead of shading above a one-dimensional number line. So in case you're curious as to what I'm talking about right now, let's look at a quick example to recall from our memory. If we had something like x is greater than 3 and x is less than 7. Very, very simple example. We take a look at a number line. We put 3 and we put 7 on a number line. Everything greater than 3 is open circle, shaded to the right. Everything less than 7 is open circle, shaded to the left. We look for the overlap of these two sets, which happens to be between 3 and 7 exclusively, so no endpoints are included here. And that's our solution set in blue. So again, we look to see where we shaded, and where was the overlap of the shading? It was between here. So we're going to do the same thing, but now we're going to do it on a coordinate plane. Okay, let's start with our first example here. We're going to graph 3x minus 2y is less than or equal to 8. Now, again, you could graph this by any means. You could take a look at the intercepts using intercept method. You could put into y equals mx plus b form to find the slope in y-intercept. Or you can just use, since it's in standard form, find the slope right away. And the slope here is just going to be m equals negative a over b, which gives us negative 3 over negative 2, or simply 3/2. So there's our slope for this line. Now if we could identify the y-intercept, or at least one point really, we could graph from there. It doesn't matter. I'll choose the y-intercept because it's easy. So set x equal to 0 to find the y-intercept. So 3 times 0 minus 2 times y less than equal to 8. This drops off. We divide by negative 2. So y less than or equal to negative 4. Now, don't worry about this less than or equal to sign right now. We'll take a look at that in a moment. So what I want you to do is go back and erase these and just fill them in for now with equal signs, as if this was an equation instead of an inequality. And we'll talk about the similarities between linear inequalities and linear equations. So this is our y-intercept, so that happens to be 0, negative 4. So those are the two values we're going to use, the slope and y-intercept, to graph this. So let's go ahead and pull up a graph and take a look. And on our graph, we're going to see that we're going to label our y-intercept down here at negative 4, and our slope is 3/2, so we go up 3 and over 2. We go up 3 and over 2. And we continue to do this. Let's remember to also label our axes and our increments, showing that that's 1 and that's 1. So let's connect our dots here. Okay, and there's our linear equation. And what I want to look at next is this. See that we have less than or equal to? This is going to be similar to what we did with the number line. If it was less than or equal to, or if it was greater than or equal to, we knew that we closed the circle on the number line. It was inclusive. It was included in the solution set. So here, because this is less than or equal to, or it could be greater than or equal to either one, I've made a solid line on the graph showing that this line is included in the solution set. But if this were just a less than or just a greater than sign, we're going to use a dashed line here to represent that this boundary is not included in our solution set. And you'll see what I mean by boundary now. Let's take a look. What we want to think about is the fact that this line splits up the graph into two regions. This is like region A, and this is region B. We need to know, should we include region A or region B in our solution? Because clearly this is not just a line anymore, it's an inequality. So let's test a point. Just like we tested points on our number line when we solved by graphical methods, we'll do the same thing here. The easiest point to test always is the origin, provided it doesn't lie on the line. So we have the origin here. Let's test 0, 0. So we get 0 minus 0 is less than or equal to 8. Is 0 less than or equal to 8? Well, yeah, sure it is. That means that this side of the graph is part of the solution set. If you tested any point over here, it would be in the solution set. So what we have to do is we have to actually just shade this portion of the graph. And that is our solution set. Example 2 says graph the solution to the system. So here we're going to have two different equations we're going to need to graph on the same set of axes. And what we should remember is that we approach this the same way as the last one, but now we're going to look at two different linear inequalities. So we're going to see that there's going to be two shaded regions, and we're going to try and find that overlap of the shaded regions, just like we did with our inequalities with one variable on a number line. So let's start by taking a look at the graph of what this looks like. For the first linear inequality, let's graph this by using intercept method, just because it's in standard form and it's pretty simple numbers. So to find the x-intercept, again, we set y equal to 0. So drop this off. To find the x-intercept, so divide by 2. You're going to get x is 1/2 for the x-intercept. And then for the y-intercept, we need to remember to set x equal to 0. And if you set x equal to 0, we're going to get y is 1 for the x-intercept. So again, when you're finding the intercepts, treat these inequalities as if they're equations, actually. So those are the intercepts for the first one, so we can just graph that by using those two quantities, or those two coordinates, rather. And now for the second one, let's use slope y-intercept, because the slope is clearly 1 right here, and the y-intercept is clearly -3. So we can go ahead and take a look at our graph now. So the first one, we'll use red, okay, for this first one up here, just so we can see the difference. So the x-intercept is at 1/2, and the y-intercept is at 1, which puts these very close to one another, actually. But let's take a look what that graph will look like. Notice for this graph, I use the dashed line to indicate that this boundary is not included in the solution set. And the last example is a solid line because it was a less than or equal to or a greater than or equal to symbol. But this happens to be just a greater than symbol. So the answer, or the solution set region, does not include the actual boundary or the actual line there. But for the second one, which we'll do in blue, we're going to see that this actually is included because it's less than or equal to. So our slope, again, is 1. Our y-intercept is -3. So here's our y-intercept down here, and our slope is 1. So we go up 1 over 1, up 1 over 1. Okay, we'll see that here's our slope. And we're going to use a solid line. Now, if we want to find out where the solution is, we need to test a point on both of these different inequalities. So let's use red first. For the red one, let's test the origin, which is right below the line there. That red dashed line, the origin happens to be just below it. So when we test it, we get 0 plus 0 is greater than 1. Is 0 greater than 1? Well, 0 is not greater than 1. So we're not going to shade that side. So we're going to shade this side over here. So we shade this whole region in red. Next, we then go to the blue equation, or the blue linear inequality. Let's test 0, 0 here as well. If you test 0, 0, you're going to get -3. So putting in a 0 here and a 0 here, you're going to get -3 is less than or equal to 0. Well, that is true. So the answer for this one is on the side of the origin, so we shade the side that does include the origin. And what you want to notice is that there's only one region that has an overlapping of these two sets, and that's where you see that crosshatch region on the top. So this is our solution set, where the blue and the red lines overlap one another. All these other regions, this region over here, this region over here, this region, so there's 4 regions, obviously, right? 1, 2, 3, and 4. These 3 are not part of the solution set. These happen to be part of the solution set for one of the inequalities. This is the overlap of the two solutions. This is nothing for either of the inequalities, neither solution. So again, here is our solution set, expressed graphically. Okay, the last example here, very similar to the previous one, but now we have some sort of domain restrictions. So we still have 2 of our inequalities, but we also have these statements here, which we can think of as vertical lines. Remember, if this were x equals 6, it would be a vertical line through 6. X equals 3 is a vertical line through 3. But we have less than and greater than symbols, so we have to consider them as inequalities now. For those, I'm going to leave for a moment. Let's take a look here. For this one, we're going to see if we want to find the x and y intercepts. They both happen to be 4. The x-intercept is 4, 0, and the y-intercept is 0, 4. That's just by setting x or y equal to 0. So that's a pretty easy one to graph. And this one happens to be in slope-intercept form already, so we're good to go there. So what we should really do is consider the fact that we have these restrictions right here on our actual graph. Okay, those are restrictions. So let's import a graph and take a look. So I'll start by graphing the restrictions using a black line so we can see that we have some boundaries. So everything that is less than or equal, or sorry, less than 6. So we have to go over to 6. So this is our x-axis, this is our y-axis. 1, 2, 3, 4, 5, 6. So we should put a dashed line here. Okay, that would be the line for a linear equation. That would be the line x equals 6, but since it's less than 6, we know we have to put a dashed line. And at 3, we have to put a solid line. So, based on these two statements here, we know that our solution set has to lie somewhere in here. Because it's less than 6, which is everything to the left of this. We mean the test points, because clearly less than 6 just means everything left of this. Greater than or equal to 3 means it's to the right of that. So what's in between here is this little narrow strip. So no matter what, this is where our solution set will lie. This is already out of the solution. This is already out of the solution. So this is literally telling you can only go from 3 to 6 along the x-axis, not including 6, because it's a dashed line there, less than 6. So let's look at our other equations, though. We'll do the next one in blue. Okay, let's do this one in blue. So our intercepts are 4, 0, and 0, 4. So there's 0, 4, and here is 4, 0. This is a dashed line because it's just greater than. Okay, and then finally, the last one we'll do in red. We're going to notice here for this one, we have a y-intercept of 4 and a slope of negative 1/2. So there's the y-intercept again. It's on the same spot as the previous one, actually. But a slope of negative 1/2 puts another dot, go down 1 over 2. So this is going to be a little bit less steep. This is going to be less than, so it's going to be another dashed line. So for this one now, we're going to notice that we've got an interesting problem. We've got the fact that the solution must lie somewhere in here. We already said that. It's got to be in there. So we, in the end, have 1, 2, 3 regions to test. So we can test up here, test in here, or test over here. So it's important that we pick the correct point now. I would choose this point right here to test the inner region, because this happens to be one of the points along the x-axis. This is 4, 0, so let's test 5, 0 to test this region here. So let's test 5, 0 in this one. 5, 0 would tell us that 5 is greater than 4. Well, that is true, so that might be it. Now let's test it over here. So if we test 5, 0, put a 5 here, negative 1/2 times 5 is going to give us negative 2.5 plus 4. And since y is equal to 0, we put a 0 over here. And we have, is 0 less than 1.5? Well, yes it is. That's definitely true. So that middle region works for these two. So that middle region is going to be our solution set. So what we're going to do is we're going to go ahead and shade that middle region right there. Okay, and we're going to put a letter S over it to represent the solution set. And what you would notice is this. If you test the point up here, pick another point. So we could pick like 5, 3 or 5, 4. This would not work in both of these, because if you put 5 and 4 in here, okay, you would get 9 is greater than 4. Well, that's true, but the next one you try it in would not work. Put a 5 in here, and a 4 in here, you get 4 is less than 1.5. Well, that's not true. So this would not work for one of them. And this one here, test the point over here. Try like 5, negative 2. 5 plus negative 2, well, that's not bigger than 4 because that's 3. 3 is not bigger than 4, so this one doesn't work for this equation. So again, this region fails on this test. This region fails for this test. This region happens to pass both of these tests. So that is indeed our solution. Your homework from this section is from 3.7. The review problems on page 139 and a review problem from section 2.3.